Hello, I am Pranavin Raj from Department of CSCAML. Today I am going to discuss about topic discontinuous multi-layer waveguides to more 2LD photonic crystal structures. In this, we are going to explore resonance modeling in photonic crystal surface emitting lasers (PCS ELS), introduction to phonetic crystals. Definition of phonetic crystals. Phonetic crystals are engineered materials characterized by their periodic variation in their direct dielectric constant or refractive index. They influence the propagation of light similarly to how semiconductors affect electrons, creating photonic band gaps, frequency ranges where light cannot propagate through the structure. This periodicity can exist in one, two, or three dimensions, allowing versatile application in controlling light emission, guiding, confinement, and filtering. The photonic crystals, they are artificially precisely structured materials designed to manipulate electromagnetic waves, creating regions where certain wavelengths are forbidden due to destructive interface caused by their periodic dielectric structure. These band gaps enable applications like high reflectivity mirrors, advanced optical fibers, sensors, and potentially optical computing devices. There are some key features of photonic crystal that we are going to discuss. The first key feature is band gaps. Wavelengths with these gaps are reflected or blocked, enabling selective control over light propagation. Periodic structure. The geometry at the wavelength scale 1D, 2D, or 3D dictates the photonic behavior like defect modes or waveguide. And next thing is manipulation of light. They allow confinement, localization, and enhancement of light matter interactions crucial for LEDs, lasers, and solar cells. There are some applications of photonic crystals. These structures are used to photo, photovoltaic devices in optical fiber, filters, sensors, and waveguides. Their ability to control light at specific wavelengths open technological avenues for energy harvesting, telecommunication, and quantum information processing. In summary, photonic crystals are artificially fabricated periodic dielectric structures that manipulate electromagnetic waves, creating photonic bands and enabling advanced control over light behavior for numerous cutting edge applications. The multi-layer waveguides structure and function of multi-layer waveguides. Discontinuity in multi-layer waveguides are interruptions or abrupt changes in the waveguide structure that affect electromagnetic wave propagation, causing reflection, scattering, and mode conversion. These discontinuities can arise intentionally for functions like impedance, matching, or filtering, or unintentionally due to mechanical transitions. In multi-layer waveguides, such discontinuities require careful analysis, often using finite element methods to characterize their scattering parameters, which describe how much energy is transmitted or reflected at the discontinuity, and the role in getting electromagnetic waves, periodicity, and resonance behavior. The discontinuities in wave. What is discontinuities? In multi-layer waveguides are interruptions or abrupt changes in the waveguide structure that affect electromagnetic wave propagation, causing reflection, scattering, and mode conversion. Types: abrupt changes in refractive index, geometry, or periods. This impacts on mode propagation and scattering. When connecting these multi-layer waveguides, to mode 12D photonic crystals, which are two-dimensional photonic crystals with periodic dielectric arrangements. Discontinuities play a critical role in mode coupling and transmission efficiency. Photonic crystal structures create photonic band gaps that control light propagation based on wavelength and direction, and the geometry and index contrast define their behavior for transverse electric and transverse magnetic modes. Discontinuities at the interface between waveguides and these photonic crystals can cause mode mismatch, leading to reflection and excitation of higher order modes or scattering losses. Impact on mode propagation and scattering. The transition to 2D photonic crystal structures is understanding mitigating the effects of discontinuities is essential for efficient integration of multi-layer waveguides with Model 12D photonic crystals structures. This involves designing interface to minimize reflection and optimize mode conversion for the desired modes, leveraging numerical methods and physical insights into wave behavior at the boundary. This integration enables advanced photonic devices with precise control over light, useful in optical communication, sensing, and quantum technologies. The explanation of mode 2 likely referring to a specific model analysis in 2D PCs. How modes are defined and analyzed. Importance in laser design emission control. Quasi-analytic modeling approach. Description of modeling technique used. The quasi-analytic modeling approach is a semi-analytical method used to study complex systems like photonic crystals by combining analytic approximations with numerical methods. This approach strikes a balance between fully numerical simulations, which can be computationally expensive and less intuitive, and purely analytic models that may be too simplistic for realistic structures. In context of photonic or quasi-periodic photonic crystals, quasi-analytic models often leverage perturbation theory and approximation analytic expression to capture key physical phenomena such as band structure, localized modes, and scattering, while using numerical solvers selectivity for interactable parts of the program. This method enables efficient and insightful evaluation of optical properties without exhaustive computation. For example, in modeling Mode 12D photonic crystals or quasi-periodic multilayer structures, a quasi-analytic approach may analytically describe the periodic layering or symmetry properties and then numerically define details like defect states or interface discontinuities. This hybrid strategy provides accuracy, physical insight, and faster parameter sweeps useful in design and optimization of photonic devices. In summary, quasi-analytic modeling in photonic integrates simplified analytic models with targeted numerical computations, enabling practical yet rigorous analysis of complex photonic structures with manageable computational resources. Application of PCLAs. How this modeling aids in designing PCLAs. Control over emission patterns and efficiency. The real world examples are stimulation, manipulation of light, periodic structure, band gaps. Key features: geometry in band gaps, wavelengths within these gaps are reflected or blocked, enabling selective control over light propagation. Manipulation of light, they allow confident localization and enhancement of light matter interaction, crucial for LEDs, lasers, and solar cells. In summary, challenges and limitations are limitation of quasi-analytic method, There are sensitivity of fabrication errors, computational trade-offs in quasi-analytic channelization by photonic crystals. Conclusion and works. Potential for expanding of 3D structures. In summary, photonic crystals are artificially fabricated periodic dielectric structures that manipulate electromagnetic waves, creating photonic band gaps and enabling advanced controls over light behavior for numerous cutting edge applications. I hope you understand this. Thank you.